This type of problem has appeared at least on 2 past exams, and so it's a good one to know how to work. It involves equilibrium of forces as well as Coulomb's law. 3 times 10 to the minus 2 kilogram spheres covered with aluminum foil are suspended on a string 0.19 meters long. The spheres have equal positive charges, and the electric force holds the spheres apart a distance of 0.033 meter as shown. Find the charge on each sphere. A word about this diagram: it is not drawn to scale. You can see that, as indicated, there's a 5-degree angle between the vertical and each of the strings. In fact, if you were to set up a triangle, an isosceles triangle that has lengths of 0.19 meters and the base of 0.033 meters, you would find that those angles are actually 4.98 degrees. But 5 degrees is good enough for our purposes. However, a 5-degree angle is very small to sketch, and so your authors have extended that angle a bit and indicated that it's 5 degrees. We're trying to find how much charge is on each of those spheres. There are several forces that are acting on the spheres. Let's sketch a free body diagram of the spheres, and then let's see if we can figure out the amount of charge through the electrostatic force that's acting, because the forces are in equilibrium. And so if we can figure something out about the forces, then we might be able to figure something out about the charges. I will concentrate on both spheres, but it will turn out that we need to examine only one of them in order to solve the problem. So here are free body diagrams. These 2 dots represent the 2 masses. Let's start with the string force that pulls each of them up. I'm going to call those forces Ft, the tension that's in the string. There are some other forces as well. There's the weight force, which pulls each of the spheres downward. Since they tell us what the mass is, we could actually come up with a number for the weight force. And in fact, we're going to need to do that in order to solve this problem. So we can get a number for the weight. The weight is equal to the mass times 10 meters per second squared. Now there's one other force, and that force is the repulsive force each sphere feels as a result of the presence of the other sphere. The left-hand sphere gets pushed to the left as a result of the presence of the excess charge on the right-hand sphere, and likewise the right-hand sphere gets pushed to the right as a result of the charge that's on the left-hand sphere. So I'll indicate that. Now, technically, I could talk about the electric force on the left-hand charge, Fe with a subscript L, or the electric force on the right-hand charge, Fe with a subscript R. And likewise, I could talk about the tension on the left sphere, Ft with a subscript L, and the tension on the right sphere, Ft with a subscript R. And with the weights as well, the weight of the left-hand sphere, Fw sub L, and the weight of the right-hand sphere, Fw sub R. It turns out that this is a symmetric problem. So whatever happens to one is going to happen to the other. So I'm just going to concentrate on one particular sphere. Now, these spheres are in equilibrium, which means that the vector sum of the tension, the electric force, and the weight all have to add up to 0 because there's no acceleration going on. I could imagine resolving this tension force into vertical and horizontal components with a coordinate system centered on each sphere, and then I could talk about the vertical component of the tension force and the horizontal component of the tension force. I think I'll do that. We can then look at forces that are only straight up and down or to the left and to the right. I'm going to focus on the right-hand sphere, so I'm going to start with a coordinate system that's centered on that sphere. I want to take this tension force and to resolve it into an Fty and into an Ftx. Let me notice where the 5-degree angle is. Then we'll resolve the force. I would like to write Fty and Ftx in terms of Ft and some trig function. And I notice that the Fty is touching the 5-degree angle. In other words, it's the adjacent side of that force triangle, and so it's going to be related to the cosine of the angle. And likewise, Ftx is not touching that angle, so in the force triangle, it is the opposite side of that triangle, and so it's going to be related to the sine of that angle. Now, some of you may be able to spot the solution, but let me talk through it. I claim the weight is balanced by the y component of the tension, and that the electrostatic force is balanced by the x component of the tension. I can get a number for the weight. So that means I can get a number for the y component of the tension force. And since I know how that y component is related to the hypotenuse of that tension triangle, I can get a number for Ft through the cosine. If I can get a number for Ft, then I can figure out what Ftx is. I can get a number for that. And if I have a number for Ftx, that's going to tell me what the electrostatic force is. And that electrostatic force is related to the charges that holds the spheres apart. So I can get a number for the electrostatic force, and then through Coulomb's law, I can figure out what the charges are. So let's go through and figure this thing out. First of all, let's figure out what the weight is. And they told us the mass of each of the spheres. I get that the weight is equal to 0.3 newtons. Since the weight is equal to 0.3 newtons, and since the sphere is in equilibrium, then that means that the y component of the tension force is also 0.3 newtons. Now from that y component of the tension force, I can figure out what Ft is. So let me work on that. I have that Ft times the cosine of 5 degrees is equal to 0.30 newtons. So now let me divide both sides by the cosine of 5 degrees and get a number for Ft. And now I'll feed these into my calculator. And I get that the tension is essentially also 0.3 newtons. I'm going to hang on to these decimal places in my TI-89 calculator because it's able to do that. Now, if Ft is equal to that number, then I can figure out what Ftx is by multiplying that number by the sine of 5 degrees. Let me do that. So let me feed in the numbers, and now I'll put them into my calculator. And to 3 significant figures, I get a number for the force in the x direction that's due to the tension, 0.0263 newtons. So let me add that to my force diagram up above. Well, if that horizontal force is equal to 0.0263 newtons and it's pulling the sphere to the left and the sphere is not accelerating, then that must mean that there's a horizontal force acting to the right due to the electrostatic force that's also equal to that number. Let me write that in. Now what's the source of that force? It's the Coulomb repulsion between these two positive spheres. So I have a number for that force. We're trying to figure out what the charge is. I know what the separation of those spheres is, so I know what R is. And I know that each of the spheres has the same amount of positive charge on them. So I can call that charge Q. So I can write down a relationship for the force and the charges, which is Coulomb's law. Let me sketch that down. Now, where did that Q squared come from? Well, it came from the fact that I've got K times Q1 times Q2 divided by R squared. But they told me that I've got equal amounts of charge on each sphere. Now I've got the problem licked. I know a number for Fe. It's 0.0263. I know a number for K. That's 9 times 10 to the 9th. And I know a number for R. That's 0.033 meters. Let me figure out what Q is. So I want to solve this equation for Q. If you'll permit me, I'll do a couple of steps of algebra in one here. So I multiplied both sides by R squared, divided both sides by K, and I took the square root of both sides. Now what I want to do is solve that equation by putting the numbers in. So here go the numbers. And now I'll feed them into my calculator. And I find that the charge is 5.64 times 10 to the minus 8 coulombs. Isn't that cool? I think it is. Let's review what we did. We had electrostatic force, tension force in the string, and weight that are in equilibrium. From the weight, we were able to find the y component of the tension force. From the y component of the tension force, we could find a number for the tension, and then we could find what the x component was. That gave us what the electrostatic force was, and then we fed that electrostatic force into Coulomb's law and solved for what the problem was asking us, the charge. So that's an introduction to Coulomb's law. These problems are not so easy when there are vectors involved. We just need to keep our heads on in order to solve them. A lot to think about at one time, but there it is. That's it.